All right, so we'll walk back in time a little bit. When we first started collecting data, way back in the early 1900s, we thought that matter consisted of particles, and we call these particles atoms. They're tiny little particles, they have mass, they have a position, we can kind of locate them, or we can kind of study the arrangement of the atoms, whether it's solid, liquid, gas. We thought of matter as being something that consisted of particles. Energy, on the other hand, consists of waves. We don't say that heat energy has mass or light has mass. We also don't think of it as being localized. We don't look at the position of light waves. They're constantly moving. So position cannot necessarily be determined. However, let's look at Albert Einstein. Papa Einstein here proposed this idea that what if electromagnetic radiation did have particles? What if it was like a stream of these energy packets? We're going to call them photons. And these photons carry a specific amount of energy. This led to a theory called wave-particle duality, which said that, we think that energy, different kinds of energy, electromagnetic radiation, it can have property of both waves and particles. We can calculate the wavelength and the frequency of red light or blue light. But now Einstein's also saying that maybe that light is also made of these particles. We're going to call them photons, or like little energy packets. Crazy wild, huh? Okay, so Einstein is known for this experiment, among other things, called the photoelectric effect. And we'll walk through it here, and then I'll kind of give you a visual. It refers to this idea that electrons are emitted from the surface of a metal when light strikes it. Okay, not such a wild concept. If I shine different kinds of light at the surface of a metal, I should be able to remove electrons. Okay, so here's what he did. He looked at varying a couple things. One was the frequency of the light, and he found that there was this threshold frequency, this minimum amount of energy that seemed to be required in order to remove electrons. How did he know that electrons were being removed? Moving electrons will create an electric current. So he was looking for electricity to be conducted. But he found that if the frequency was below this threshold, we had no moving electrons and then no current. Alright, for light with frequencies greater than this threshold, the number of electrons emitted by the metal increased. I should say, number one, we started releasing electrons, but then it also increased with the intensity of light. So in the middle here, here's kind of his big findings. If we were below the threshold, we had no electrons emitted, regardless of the intensity of the light, how bright it was. If we were at or above the threshold frequency, we started to see electricity conducted, meaning that electrons were being removed from the metal surface, and the number of electrons removed increased as the intensity of the light increased. Awesome. He also noted that for light with other frequencies that were greater than the threshold, the kinetic energy of the electrons increased with the frequency of the light, which means that these electrons are just moving faster, which again conducts more electrical current. So the two things that seem to conduct more electricity were either greater frequencies, that gets more electrons moving and they get moving faster, or increasing the intensity of the light. Then I seem to, again, get more electrons and more photons emitted. Here's one visual. Let's say we had low frequency light. So I don't know, maybe this is kind of red light. Cool, red light. So that's low energy or low frequency. When that red light hits the metal surface, we had no current. Measure of current. because I had no electrons moving. This light is not high enough in energy to remove electrons, which again is just kind of showing that light comes in these specific quantities of energy. Red light being low energy. So now as you increase the frequency of light, let's say we go to like a blue or a purple, violet. Yeah, it's crazy high energy. So this is going to be like maybe violet or purple or whatever you want to call it. A higher energy color of light. Now I start removing electrons. Those moving electrons start creating an electrical current. And now this last little picture at the bottom kind of shows what happens as we increase the intensity of the light. As we add more photons, meaning that the light is brighter, I got more electrons emitted from the metal surface, which just shows we have more current. So here was kind of like the low intensity. So maybe it was not as bright, less photons. And now I'm getting a higher current. I'm getting more electrons removed, which conducts more electricity. So you can kind of tell as we compare these two, they must be about the same frequency. I mean, the diagrams look to be about the same frequency. But as I increase the amount of photons or the intensity of the light, I remove more electrons. And that again creates more current. Again, if you're kind of a visual person, here's a good, I guess it's kind of a good little visual. It's kind of a fun game to play. We can choose different metals. This one is set to sodium, which is kind of fun as long as we don't have water present, right? We can keep that on sodium. I guess I don't mind that. Okay, so let's start playing with the frequency of light. So right now I've got, well, I guess it's kind of on infrared. And I have no current being conducted currently. Okay, so let's increase this. Let's see if we can find the threshold frequency. And let's set this intensity. Let's turn the light on. Let's go like 50%. So here's like the brightness. So again, like if I increase the intensity, I make the light brighter, which we'll do in a second. That's going to be awesome too. First, let's play with the wavelength, the frequency and the wavelength. Let's see if orange light. Nope, not high enough in energy. So again, this is all just kind of proving that these different forms of light carry different quantities of energy. These photons, these energy packets, have different amounts of energy. Yellow, no, that's not enough. Green. Oh, look at that. So somewhere in this green light area must be my threshold frequency, where now I'm finally starting to get electrons removed from the surface of the sodium metal. Awesome. Now the current being conducted is very small. It's actually still even registering at 0. Let's see if we can bump that up a little bit. Oh, there's like some light blue. There we go. So now we're finally starting to register a current. And I can tell that there's more electrons being removed from the surface. This is higher energy. And as I keep increasing this frequency, look what happens to the kinetic energy of the particles. Can you tell they're kind of on average, they're moving faster? There's a few slow pokes in there. But let's say we even go into the UV spectrum. And can you tell that they're moving faster? My current is increasing. The energy level is increasing as I increase the frequency. So maybe the threshold was somewhere in that green range. That's where I first started getting electrons removed from the surface. Okay, so let's bring this down, and then we can look at the other variable, which was the intensity of the light. Oh, I don't know. Let's maybe bring it down. Oh, this is kind of a pretty color. So let's go into this kind of blue range, where I've got these electrons Actually, let's up it a little bit so that we're registering a current. Okay, so here we're starting to register a low current. Now let's increase the intensity of the light. So now this just means that we're making the light brighter, which means there's more photons. More photons should carry more energy. So here the light kind of looks like it gets darker. And can you tell there's more electrons being removed? And as I take this back down, again, I can kind of tell that there's less electrons. They move slower. Let's bump this one up a little bit. And again, I can tell too, like here I'm getting a good current if I take this intensity way down. So can you tell the light's getting dimmer? I don't have enough photons. I don't have enough energy to start removing electrons from the surface of the sodium metal. So I have to increase the intensity of the light, which means that I'm adding more energy. And now you can kind of tell that light's getting darker. And notice too, that when we're setting the intensity, I'm keeping the wavelength and the frequency the same. It's the same color of light. So as we get more photons, there we go. Those photons will increase the energy level, and I start removing more electrons, which starts to conduct more current. So this is all considered the photoelectric effect, where Einstein is studying the relationship between energy levels, intensities, and this threshold frequency of light that it takes to remove electrons from the surface of a particular metal. So now again, he's saying that these photons of light carry different amounts of energy.